With that setup, I think I can tell you how the simplex algorithm works. Not in all full details in how it's implemented, but enough that you could, I think, work out the details if you wanted. And I realize some people have seen this before, maybe not in exactly that way. Everyone explains it a little different. I'm going to do a combination of two explanations. First is I'm trying to give you a geometric intuition, because really LPs are not that hard. It's a very simple concept if you look at it from this perspective. So here I'm going to take this first normal form where we have less or equal constraints. And potentially many of them, many more than variables, and it still makes sense. Again, here to make things simple, n is 2, so the number of variables is 2. I can still point it, draw it in the plane. Each of these constraints, less or equal in 2D, is essentially one of those lines plus a direction, which is not drawn, but all of those kind of point in some way. And to make the picture look sensible, I guess you have to point them all in this way. So an individual constraint is basically telling you everything on this side is okay. If you take the intersection of all those half spaces, then you get some specific feasibility region. So here for notation, I'm going to write hi for the half space of one constraint. So all the values or all vectors that satisfy this constraint. Okay, but really it's the area below a line or above a line in this case when n is 2. And then the intersection of all these gives you this feasibility region, the yellow part. In this case, again, I'm assuming that these all point towards the yellow bit, which is not drawn in the picture. You can also see from the picture there's some constraints, like in our Hesse-James example, that don't even contribute to the feasibility region. They're redundant. Whereas the actual contour of the feasibility region is formed by potentially many constraints. Okay. Now, what about the cost function? In general, the cost function, I drew it before as this dashed line. And it's in 2D, it's some line with a certain slope, but I can always, visually at least, think of rotating my picture so that this dashed line is a horizontal line. Okay. Now, how to do the rotation with linear algebra math, I don't care for now. You can just change it to a different base. But suppose for now, or maybe make it an assumption that the orange line is horizontal, which means if we move the objective value up and down, we move the orange line up and down, which means the optimal value will be the lowest point in the feasibility region. And so you can physically imagine you put some marble in this yellow space and it'll just fall and roll down to the lowest point naturally. And here, clearly, it will end up here. Okay. And again, in 2D, this is very simple, but this actually works in general in just the same way. C itself, so brush up your linear algebra memory. A vector in full dimension defines a hyperplane, namely all the, for example, all the vectors that have scalar product 0 with it. And the same vector is also the normal vector standing on that plane. And that's really what this green arrow is. So this is the hyperplane for C, and that's C itself. It's pointing downwards. So really C you can think of as a direction for improvement. That's where you have to move. And this works in any number of dimensions. So this is already showing a bit what the algorithm does, but imagine you have a marble that somehow sticks to the boundary. Then it would still roll down step by step until it stops in the optimal point, just following gravity, or imagine a magnet pointing downwards. Okay, if you take enough half spaces, I guess this is hyperplane, not half space. Half space is everything below a line. The hyperplane is the generalization of a line. And if you take n such lines, here 2, then you get a single point. Now, what's the connection between half space and hyperplane? The half space has some boundary, and that's a hyperplane. Here, half space is some line below, and then the line is the line, the boundary of the half space. So if you take n of these, you always get a unique point. In this case, take any 2 constraints, and you get the intersection point. Again, this also works in higher dimensions. And this intersection point is what we call a vertex. It could be outside of the feasibility region. It could be here, or it could be one of the vertices of the feasibility region, if you think of it as a polygon. Let me use the same name. But really, it's just the intersection of these hyperplanes. I guess that's a bit wrong. These are the hyperplanes, not the half spaces. They don't necessarily have just a single point at the intersection. Just from the picture, from the physical intuition, if you have some point in the interior of this yellow region, you can always move it freely in all directions. So in particular, you can move it in the direction of the improvement, the green arrow. So you can always improve it further. So it's never going to be an optimal point. On the flip side, that means you can always find an optimal point that is a vertex. The only other option would be that you have a whole edge that is optimal. Any point on that edge is optimal because you have a wall that's horizontal in that picture. But then still the endpoints of that wall would also be optimal. So in general, you can say there's always an optimal vertex. Could be many, or it could be several. So the optimal objective value is given by the value of some vertex. So that's this xi star. And that gives you some, now we finally reduced this annoying continuous problem that I'm always a bit iffy about, not sure how to solve it, into something discrete, because there's only so many intersection points, namely as many ways as I have to, as I can select n hyperplanes from all the constraints. So these are all the vertices, and in principle I could just go through all of them. And if n is small, that's actually polytime to brute force all the vertices. It's not how you want to solve this, because in general n can be big. I said millions in the beginning, so certainly you don't want to do m to the 1 million. But if n is really small, like in our examples, it's one option. And that's what the simplex algorithm does in a more clever way. It doesn't brute force all the vertices, but rather it starts at an arbitrary one and then always finds a neighbor that is better. And that means it follows some path along the contour and will stop as soon as there's no better neighbor. And then we found an optimal vertex. And what does a neighbor here mean? It means that it's defined by an intersection of hyperplanes where only one hyperplane is different. You throw out one and you add another in. Okay, that's the geometric view. And you can write this as an algorithm. We're given the half spaces, and then you can conveniently say if their intersection is empty, the problem is infeasible. Otherwise, you find some feasible vertex. How to do that is another round of simplex. Let's ignore that for now. So suppose you're starting here with your x, and then you look if X can be improved or if the green direction is hitting a wall, is going against some constraint. If that's not the case, then you can locally improve it. And so if that's a funny bit, if all the neighbors that are feasible are actually strictly worse, but you still can't locally improve, then the problem is unbounded. That case is a bit more tricky to see. That needed another picture, but let's ignore that case for the intuition. The typical case is there is some way to move in the direction of the green line to a neighboring vertex, and then you go there and repeat. Okay. Now this is a nice way to visualize things, and oftentimes you get the right intuitive ideas. For example, we can't necessarily say how many points we visit if we follow such a contour. And indeed, this is in general a problem of simplex. You can find contrived examples where there is exponentially many vertices, and you can also make simplex go to visit exponentially many vertices on its way to find the optimal solution. So oftentimes the geometry gives you the right way to think about the problem. If you wanted to implement it, it's not suitable. For that, you want to bring back linear algebra. And so I want to briefly introduce that other side of things, which is probably closer to what you've seen if you've seen it. The way I'm going to present it is take the other normal form now with equality constraints. That's a bit easier to work with because now really you can work with these equalities, and all that is left of the other constraints is a non-negativity constraint. That means we have now many more variables than constraints necessarily to make the problem interesting. If that's not true, the problem is essentially either infeasible or has a single point, or that's easy to solve in all cases. So you should think now that there's many more variables than constraints. And now we talk about the matrix A from linear algebra point of view. And for example, for starters, we'll assume that it has full rank. So remember, because M is now smaller, the matrix A is wider than tall, because this is M and this is N. And so rank M means essentially that whenever you, or if it's non-degenerate and has full rank, whenever you pick a collection of columns, M columns out of the N possible ones, you get a set of linearly independent vectors. That's in general not true, but if you assume that the problem is such that you don't have redundant constraints, or things are not, there's constraints that are either multiples of each other or they intersect several in a weird place. If you kind of ignore all these corner cases, then you can pick any collection of columns and you get a basis for the matrix, which means just M independent, linearly independent vectors. Now, you can split up your variables. So again, remember, J is a collection of columns, maybe these four. And then you can identify the corresponding variables that would be put on those columns as xj. These are the basis variables, those that interact with these columns. And you can separate those from the others, the non-base variables, just by their index, right? The basis variables have an index in this capital J and the others don't. Now, why is that useful? You can rewrite some of the things in splitting up the two parts to make progress. You can split up the constraints. So again, you take the matrix and now you take those four. That gives your matrix AJ. It's a square matrix now. And all the other columns together form this matrix AJ bar. And you similarly do that for the constraint, for the objective function coefficients. Then what we get is any feasible vector, so any x that satisfies the equality constraints, you can just rewrite, you split up that large sum into the columns that have index in capital J and the others. And so now this matrix AJ is square and has full rank, which means it's invertible. So you can find an inverse matrix, and you can multiply the equation from the left with this inverse matrix. And then these cancel to identity, and you can subtract this to the other side. So you get an expression for xj, the basis variables, as a function of the other variables. Okay? And that's, of course, it's kind of clear if you have a certain number of constraints but more variables. You can fix some of the variables, namely exactly m minus n many. As that's really n minus m here, right? N minus m many. And the other variables are then fully determined from the values you picked for the n minus m variables. Okay. Well, why is that useful? Well, in particular, you can set all the other variables to 0, and then you get a relatively simple vector x that solves the equality constraints, that satisfies the equality constraints. And these special kind of solutions, so the x's you get by taking some xj bar and setting it to 0 and computing the others from this formula here. That corresponds to the vertices in the geometric picture. Now, they may or may not be a feasible solution because in general, you don't know whether the base variables are satisfying the non-negativity constraints. They may be negative or not. But if they are non-negative, then they're a feasible basic solution. So to wrap up this slide, if you're given a selection of columns, any m columns out of the n variables, you can compute the basic solution and you can check whether it's feasible. Just check if it's larger than 0. Now the last bit is to make this step in Simplex, check if we're optimal already, and if not, make an improving step. And that is easy from where we are now. So we have this basic solution where we think of setting xj bar to 0, so this whole term cancels. How can we locally modify this existing, suppose it's feasible, how can we locally modify our solution to improve the objective function? Well, what we cannot do is easy to see. We can't take any of the xj's and modify them because we would violate the equality constraint. And we can't decrease the non-base variables because that would violate the non-negativity. They're already at 0. So the only thing is we can increase the non-base variables and then maybe see what happens to xj, if that makes it feasible or not. So we can rewrite the cost function, and that will tell us what to do. So that's the objective function. We can split it up the same way by the variable indices that occur in J and the others. Now we know xj. This is using for xj what we know about the basic solution. So you plug this in general. This is true not only for xj bar 0, but in general. Any solution that satisfies the equality constraints has this form. And now you can split up the two terms. So you have this part, which is constant, essentially. There's no x in there. And something in front of xj bar. And so this is the old cost vector, and then this new term here that combines, sorry, this shouldn't be here. That combines these parts. I guess the transpose is also wrong. Sorry. That should be just at the C. The matrix is already in the right shape. The key point here is this is some vector Cj bar. I guess that's why the transpose. So this is transpose now. You get a new set of coefficients for an objective function, and the overall objective function. Okay, I got to fix the. I'm staying here on the corrected slide. The overall objective function can be written as some constant plus some terms that depend only on the non-base variables, and these are the ones you're trying to modify. In particular, we try to slightly increase one of those and see what that does to the objective value. Well, if the coefficient that some variable here has is negative, then by increasing it, I'm only making, okay, we minimize, then I'm making the objective function better. Whereas if the coefficient is positive, I cannot help the objective value by increasing this xj. So you get no local improvement exactly if this thing is non-negative. Then any increase here would only make the cost higher, and that's not better. And indeed, that is, if you cannot locally improve, is the same as having a global optimum. That's because everything here is convex. We have a convex function over a convex domain. So whenever you have a local optimum, that's actually the global optimum. This is not true in general optimization, but because of the linearity, we get this simple criterion. You're only looking for a local optimum. And so that's essentially the end of this simplex algorithm. That's what it does. It computes these CJs. It checks if they're all greater or equal 0, then the current solution is the optimum, and you can stop. Otherwise, there must be some entry that's negative. And then you know which of these non-base variables now becomes a base variable, and you have to kick out one of the base variables to move to a neighboring vertex. And that means, so you increase this variable, and you do that until some of the base variables drops to 0. And you can compute how far that is, so you can essentially use more linear algebra to do that step in a smart way. But that's really getting into the implementation. So let me wrap up at this point. So what we've seen is the conceptual ideas behind the simplex algorithm. It's a relatively simple and mostly combinatorial and discrete algorithm. It uses linear algebra to do the computations, but it's basically talking about these discrete objects as vertices on a polyhedron. Polyhedron is the higher dimensional version of a polygon. It's fairly easy to implement once you dig through the details what the computations have to do. Implementing the implementations themselves is actually not hard. And it's usually the choice of open source solvers, just because of that. And it's also doing reasonably well anyways. Now, what I've said before, the worst case is actually an exponential. So simplex is not a polytime algorithm in the worst case. The details depend on how you do this last step. If you found some non-basis variable you want to increase and kick out another, there's usually some choice, and you have to pick a rule how to make that choice. And that depends how long it takes, but there's no such rule known that guarantees polynomial time. On the other hand, it is known that if you take any input and you slightly modify the numbers in it, you actually get an expected polytime algorithm with simplex. That's called smoothed analysis. I'm just mentioning this here because it kind of fits the theme of the lecture. But we're not going to dig into any of this in more detail. And last thing is, there are alternative methods that are More complicated, both to understand and to implement, but they are achieving this worst case polynomial time guarantee. Commercial solvers like Gurobi and so on, they often implement those, and these tend to perform best in large instances. For the lecture, all you need to take from this is a rough idea what Simplex does, and the fact that you can solve LPs in polynomial time in theory and in practice.